So good morning. Good morning. So this is the first meeting in the month of April. So last month, we discussed sp hybridization within the context of beryllium hydride. It is a linear molecule. We don't really expect it to exist. And then using quantum mechanics LCAO and invoking more atomic orbitals from one atom, at the end, we have this picture of the beryllium 2s and 2p. They mix together to form a oppositely directed hybrid orbitals. And that will concentrate the electrons density, thereby forming a stronger bond with a hydrogen on the left and a hydrogen on the right. So today we will continue our discussion after 11 days. We will do sp3 hybridization and sp2 hybridization. And then we will give some examples on real materials that this hybridized orbitals work in determining the properties. Before we move on, a few announcements. This week's sample questions are now available in Blackboard. The TA will do it today and tomorrow. It is about what we discussed this morning. All notes on the physics of molecules are now available in Blackboard. The last part will be on rotational, vibrational, and rotational spectrum. So three things. I returned all the marked midterm paper individually to you. You can receive a marked version from Blackboard. And I think the university sent an announcement to all students about the finalized timetable for all the final exams centrally organized, including our course. So please take note of the date and time. Details will be announced in the future, but it is more or less like the way we did the midterm. The coverage will be announced later, but usually it's from the beginning to the end, okay? So let's continue. The first thing we would like to discuss is sp2 hybridization. And it is better to do it with an example. So the example here is this C2H4. Here you see several standard pictures of this molecule. So this is the chemist's viewpoint. You can think about it. This one is a top wheel. So you have two carbon, and then at a certain angle, each carbon is bonded with two hydrogen and then with the neighboring carbon. And there is two lines in the middle. So this is a double bond. So this is the chemist's picture. The same top wheel can be looked at this way in a more lively picture, including something called the sp2 hybridized orbitals. You see that this is the, for example, XY plane, and then on which centered around a carbon, there are three things sticking out. These are the sp2 hybridized orbitals, and there's a directionality in which all this sp2 hybridized orbitals are extending an angle of 120 degrees. So this angle is 120, and this also 120, and so on. Whereby, again, electrons density are concentrated in different directions, and then stronger bonds can be formed with the hydrogen as well as between the two carbon. and that is a very strong sigma bond. And then at the end, there is still one PZ electron belonging to each carbon. They stick perpendicularly out of the XY plane, and then they will form a pi bond. So this is the general picture of this C2H4. Next, we would like to look at the quantum mechanics of this bonding. The first thing we would like to discuss is how the molecule formed this very rigid or strong skeleton. So we have a CC in the middle, and then 4H sticking out. So this is the top wheel, and that involves sp2 hybridization. We introduced it last month how to construct the hybridized orbitals in a systematic way. Here we extend it to sp2 hybridization. So for carbon, there are 4 electrons in the n equals 2 level. So we can look at it as 1 in 2s, and then 3 in px, py, pz. That is according to the Hund's rule. Now, what is involved in sp2 is 1s, 1 electron in the s. I mean, carbon is 2s, but 1 electron in the s, and then 1 in the px, 1 in the py. Whether you call it xy is arbitrary, but once you put it there, and then you can call this plan xy plan. So that's what I did. Therefore, we are going to mix or linear combine 2s, 2px, 2py. 3 things from carbon goes in a black box, linearly combined, and therefore 3 sp2 hybridized orbitals must come out. Next, we exercise our systematic way to construct these 3 hybridized orbitals. Last time we discussed that the S is a sphere, non-directional, and when it is going to divide itself into 3 portions in each of the hybridized orbitals, it is not going to bias any one of them. So therefore, when we write down the 3 hybridized orbitals as C1, C2, C3, the S orbitals from carbon will have the coefficient 1 over square root 3. The 3 means there are 3 sp2 hybridization. The 1 over square root 3 would mean the S, the probability of finding the electron to be in S is 1/3 in each of the hybridized orbitals. That is the meaning of not biasing any one of them. With this, we only have 6 coefficients left to determine. And the requirements or the criteria would be each one is normalized, that is easy, and then they are mutually orthogonal. So C1, C2, C1, C3, C2, C3, the inner products are 0. The inner product of themselves, that is to say normalization, is 1. So that will be sufficient to determine all the coefficients. So let's do one example. I would like to put one of them on the XY plane to be along Y. Now that is arbitrary because you put it somewhere, I rotate the XY axis, I call that, that is Y. So that is without loss of generality. So I put it in Y, and therefore the first one, the full form will be 1 over square root 3 psi 2s plus a coefficient to be determined and that can only invoke to py because I point it at y. The other one will be pointing at x. With fixing it, this one as y, this coefficient is 0. So I save one coefficient. The other one, side 2, I also put it on the xy plane. So generally, there will be two coefficients, p2 with py and c2 with px, sorry. And then the other one has the same general form. So the game now is to determine what is B1 and possibly what are the B2 and C2, etc. So the name of the game is to use the criteria. So psi 1 is normalized. So you do this, normalize it, and using atomic orbitals belonging to the same carbon, 2s and 2py, they are orthogonal by construction. So that will be easy. Without doing any mathematics, you can see this B1 is 2/3 square root. So thereby we fixed it one thing. Quantitatively, this is the first sp2 hybridized orbitals. It is this form. Okay. Now, for those who really like mathematics and graphics and computer graphics, you can take this, look up this atomic wave function and this atomic wave function and really plot the three-dimensional density of the electron out. And it is of this form, rotate through the y-axis. Next, we need to do B2 and C2. Okay, so once psi 1 is fixed, use the orthogonality requirement. You dot C2 into C1. Okay, now obviously, well, you better do it once without knowing a priori all the tricks. But if you think about it, this will multiply into that. Okay, the 2s is a self-normalized, but when this multiply into that, you do an integration inner product that will be 0, right? Because it is the same atoms, different atomic orbitals. So thereby, the only thing you need to do is this times that, okay? But B1 is now known, okay? And therefore, it is easy to determine that B2 is 1/6 square root minus sign in front. After fixing B2, then the remaining C2 can be fixed by C2 itself being normalized, and then give you the last coefficient, all right? So all in all, C2 is determined to be this, okay? So at this point, do you know the systematic way to determine a hybridized orbital? Okay, there is a question. There are two questions. I try to answer the second one because I mentioned it at the beginning. The question was, why is the coefficient of 2s 1/√3? Okay. First of all, key idea, S is non-directional. There's no direction for it, okay? And at the end, we are going to form 3 sp2 hybridized orbitals, okay? Mr. Man, follow? Okay, now knowing that S non-directional, what is the portion of itself to be donated to C1, C2, or C3? Now, first of all, it will not bias anyone, right? Follow me? Okay, And that statement already fixed it. It is 1 over square root 3. Okay, now after you write it out, you can regard this thing square as the probability of finding the electron in this C1 state to be in the 2s. And it is 1/3. Do you understand? So it is equally dividing itself. Mr. Man. Okay, so okay, get one question done. There's another one. Suppose we didn't set one of the orbitals at y. Does it mean that this equation will not give unique coefficients or unique up to rotation? Okay, now you can try that. You can try that. I think it's still sufficient to fix everything. Okay, try it, please. As you will see, later in SP3 and in today's sample question, my notes put the SP3 in somewhat strange, well, the typical form, but the TA will intentionally put one of the SP3 along an axis and then fix all the other things. So let me continue. Good. So this will help us fix everything. Now I would like to explore one physical properties. The question is, what is the physical angle, I mean in view space, between this C1 and C2 sp2 hybridized states? So this is what I intentionally put along y, and I intuitively know that this is directed towards y for the reason S has no direction, it's like a ball, and then this is along y, it's the number 8 along y, okay? And of course, this has a positive part and a negative part. This is positive, you add it up, at the end, you will get something like smaller in one direction and bigger in another direction. Therefore, you have this sp2 hybridized picture. Then we also determine the second one. The first term has no direction because it's an S. Now, I'm being lazy here, but it works. This is along y. It has a negative coefficient, so it is in the negative y direction. And how long is it? That long, okay? And then it also has an x component because this is pointing along x. And how long is this x component? 1 over square root 2. So if I use this idea, the second one, C2, is like a vector pointing in this direction. So I try to draw it out in this picture. This is C2. So the x component is positive, that much. The y component is negative, that much. Therefore, I draw a vector representing C2, okay? Now, I must say, I'm being lazy, but this trick works. Formally, it is a three-dimensional spatial structure, okay? But for determining what is the angle here, this trick suffix. So the point now is to find the angle between C1 and C2 as depicted here. So I think you know how to do it. Well, you can find this angle and then add 90 degrees to it. So you have a triangle here. You know what are the two sides, the length of the two sides. Therefore, you know this tangent theta phi is given by y over x. And therefore, you find it to be 30 degrees. Then you add back 90 degrees here. Therefore, it is the famous 120-degree angle between sp2 hybridized states. So I will stop the discussion here. I will not work out 3 for you, but I encourage you to do it for yourself. So we have this. Now you can play with the trick. This must be orthogonal to C1 and C2, and itself it's normalized, okay? So I think that will be sufficient, more than sufficient for you to fix all the coefficients. So I leave it as an exercise for you to do that, and then you can look at the angles again for yourself. So let's go back to our C2H4 example. So we have discussed a carbon can form a 120-degree extended sp2 hybridized orbitals. There are 3 of them. So this is the first carbon. Then we repeat the discussion on the second carbon. All right. Now, if the carbons are far, far away, they have no sense about what is the angle to put the hybridized orbitals. As I already mentioned several times, molecules has the special effect of having 2 nearby atoms. Therefore, there's a special direction. So here for the second one, the hybridized orbitals, one of them will be pointing towards the other carbon's sp hybridized orbitals. In doing so, this one will have a good overlap with this one and form a good sigma bond, which is strong. The other 4 will be bonding with hydrogen. Therefore, it will form a skeleton. So this is the skeleton formed with very specific angles. Okay, so we have an explanation for the structure now. The last thing to do quantum mechanically is to see what is this second line, the double bond. This is the pi bond. It has to do with the PZ, which is off this plane of the paper. It is sticking in and out of the picture that we drew. So here we will finish off the pi bond portion of the discussion. So after doing the skeleton, remember that for each carbon, there's still 1 electron in the PZ. This thing, this plan is what we discussed. This is the XY plan. We are done with this, forming the skeleton. So for each carbon, there is a PZ sticking out. Then you start thinking like a physicist. Don't do any formula derivation again, okay? Even you are a good theorist, if you do that, you are not that good at all. So now, just think about it. Okay, it is bonding again. So there must be some Hamiltonian involving. You don't even need to write it down. And then you have 2 things. 1 PZ from the left carbon, 1 2Z from the right carbon. Okay? So therefore, 2 things, LCAO again is 2 by 2 matrix problem. They are the same carbon PZ, therefore diagonally, it should pick up the atomic 2p state energy, okay? So what will be pushing these 2 atomic 2p up and down will be the off diagonal elements with PZ on the left, whatever the Hamiltonian in the middle, and PZ on the right, do the integral. So that will be the determining factor. So I don't even want to write it down. I just draw a picture. So this is the key energy involved in pushing the 2PZ state. I follow the chemistry literature's symbol. I call this thing beta. It is an energy. So this is the off diagonal element. So I call it beta, and generally the other one will be B conjugate, B star. With this, you don't need to do any mathematics. Well, you have done that if you realized in a problem set. Then at the end, there are two eigenvalues. One is epsilon 2p go up by beta, I mean beta absolute value. And then the other one is epsilon 2p minus beta absolute value. So one will go down, one will go up. Bonding is guaranteed because you only have two electrons, one from this and one from that. They all go to the lower state, thereby gaining energy, forming this additional bond. And that is the second line in the C2H4. So you see, a very simple thing actually is quite quantum mechanical. And this will take us naturally to a fascinating point about benzene. Benzene is C6H6. So we have 6 carbon. Structurally, you can do a scattering experiment to determine it. And then we have this hexagonal ring of 6 carbon. So look at here, okay? So we have this, this is a top view. See from above. So you have this carbon forming a skeleton, and noticing all this has an angle of 120 degrees. Okay, you have a lot of 120 degrees here. Thereby, it is signaling sp2 hybridized orbitals overlapping with the neighboring carbon to form this planar hexagonal structure in this, let's call it XY plane. All right. So we will not repeat the discussion on forming the skeleton. So you just extend what we discussed, sp2, for every carbon, it will form this strong skeleton. Instead, we will focus our discussion on the 6 pz electrons. Every carbon has a remaining unbound electron in the 2pz state. So look at this side view picture. After forming the hexagonal skeleton, each carbon still has one electron in this pz state to bond. Then here is a very interesting quantum mechanical question. In the past, some chemistry book will draw benzene like this, meaning maybe this two will form a pi bond. So there will be a double line here, and then the other two, the labeling will form a double bond. Therefore, you will have 3 double bonds like this. But once you draw out this, you may wonder, it will be the same as this, okay? Because this two may as well form a pi bond, okay? Then, in more modern books, you will see this one with a small circle in the middle. In the following discussion, I would like to explain to you what is this small circle in the middle. Here is a big idea that will come out. It is called delocalization of electrons, and meaning let it wander, let an electron wander around in a farther extent that may lower the energy. Okay, so that is essential to understand to the understanding of metal. In metal, you know, the so-called conduction electron are free to move around in the piece of solid. But this is the first idea. The idea that first came out from the discussion of benzene. So we would like to see why this is preferred. So again, we will exercise, think like a physicist. We don't want to derive anything anymore. We assume this skeleton is already formed by sp2 hybridized orbitals, overlap of that. So we don't worry about it. It exists. We only think about this problem, the PZ, the 6 PZ orbitals, what bonding will they form? All right. So we will do LCAO using 6 PZ orbitals, 1 from each carbon. So therefore, LCAO means I will form a linear combination with 6 coefficients C1 to C6 using the PZ, 6 of them, as the basis. Then you start cranking in your mind. There must be some Hamiltonian governing the electron seeing this structure. Okay, you can write it down, but we don't want to write it down. We just know conceptually there's a Hamiltonian. And then we have 6 bases. Thereby, we can form or construct a 6 by 6 problem. And we know the matrix elements will be Hij minus Sij. That's what we learned in week number 1. We have been repeating our skills. Okay, not much new skills, but if you are good at several selected skills, you can understand a lot of physics. So the next step is we want to write down this problem without doing any calculation. We start thinking. Diagonally, the diagonal element, Hi11, for example, should be the energy of the 2p Z state, because the atomic energy will dominate the diagonal II element. Then Sii, S11, for example, is 1 atom's PZ in a product. By normalization is 1. Okay, so we know the diagonal 1. Next, how about Sij when I is not J? They belong to different atoms, then the concept kicks in. Formally, it is not 0. Practically, it's not going to be big. Therefore, we will approximate it to 0. Okay? So that is the not much overlap idea here. Okay. So let's start to write it out. So every diagonal 1 will be the atomic energy. We will use a symbol to represent it. We will use epsilon. In many chemistry book, they will use alpha. It is called the on-site energy in different contexts. Then, the more important thing will be H1 Ij. That is the off-diagonal Hij. Now, Ij will be 2 different indices. So look at this picture. If I is 5, very naturally, the most important Hij will be 5 with 4 and 5 with 6. Now, that is the key point. Do you understand? Because separation is the nearest. You understand? Because at the end, it is like the C2H4 pi bond. There is a PZ with an H in between. You do the integral. If they are too far away, that integral will vanish. Get me? Do you understand? Okay. Now that is a very important concept. It is called nearest neighboring interaction. By interaction, we mean this Hij for I not equal j. Nearest neighbor means for 5, we only care about 5, 4 and 5, 6. We don't need to care about 5, 1, too far away. 5, 2 and 5, 3, they are also too far away from each other. Do you understand? Okay. So now with this, I will introduce a symbol. I don't want to even work out the integral. We don't need that. We can use experimental data to fix it. So we just call Hij V if they are nearest neighbors. Otherwise, Hij will be 0. That is the nearest neighbor assumption. So it is almost tridiagonal. Yes, if you move the thing around, okay, but it is cyclic. All right, you will see it on the next page. There's a question. Okay, now let's write it down, the whole thing. So 6 by 6. With this discussion, things becomes very simple. H11 equals H22 because they are the same carbon 2pz. I call it epsilon. E is the unknown. We are going to solve for the eigenvalues. There will be 6 of them, but we have 6 electrons to fill into this orbitals. Then, because of the nearest neighbor structure, number 1 will have nearest neighbor with 2 and number 6. Okay, so indeed, Tiffany, it is tridiagonal if you move them around. Okay, but there is one thing here. Do you see? Get me? Okay. Now for number 2, diagonally is the same epsilon. The P is at atomic energy, but then it has neighbors with 1 and 3, and so on. So without doing anything, you can look at the structure and write this thing down. Okay, this is equivalent to the problem of a matrix problem. This is a determinant equals 0 problem. Just to remind you, this is the same as this matrix problem. Okay, finding the eigenvalue and the eigenvectors. They are the same problem. Okay, so now try to solve it. It turns out that can be solved analytically, but I haven't done it for you. Maybe a problem set question for you. And here's the answer. So after you do it, of course, there will be 6 eigen energies. So there are 6 energies here. Immediately you see, actually, these 2 are degenerate, these 2 are degenerate. Okay, now the exercise has to do with, now we have epsilon and V in the matrix. So what is this thing? How is this related to epsilon and V? Is it epsilon minus 2V or, you know, epsilon minus V or whatever? Okay, so you have to work it out, but it must be something related to epsilon and V. I mentioned that that can be solved analytically because of the degeneracy. You have double roots, so that makes this 6 by 6 problem much easier. And there are also 2 degenerate states here and 1 very high energy here. Okay, so this is the answer after solving the 6 by 6 problem. This one, okay? You get that? That is getting the MOs, the molecular orbitals. Then we have to fill the 6 electrons, the pi electrons. There are 1 electron in each of them. There are 6 altogether. Therefore, you have to put them in according to the Pauli exclusion principle. So this is the way to put it in to get the lowest energy. What should we compare it with? If they are not coupling at all, okay, it will be epsilon, 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 epsilon without anything, not coupling. So the energy will be here on this line. So this is what I try to depict here, okay? So in doing so, energy is lowered, okay? And forming this combination of all the 6 1, the eigenfunction will be linear combination of this 6 1. Thereby, 1 electron could be found in all of these centers with some probability by the interpretation of the wave function. This is delocalizing, okay? But to be fair, we should compare with an alternative possible structure. So this double bond, double bond, double bond structure. By this structure, we mean 5 is only bonded with 6, 4 with 3, and 1 with 2. So we look at the picture and then we know what it means in terms of this 6 by 6 matrix. Number 1 only bond with 2, so you only have a V off diagonal with number 2, but you don't bond with number 6 anymore, okay? And number 3 anymore. So this is this picture, okay? And then 3, 4, 5, 6. So this 6 by 6 problem is now factorized or block diagonalized. I know someone is good at a computational thing here. Okay, so this is a block diagonalized into 3 blocks. Each block is a 2 by 2 thing, so push up, push down. So for example, you take this one, you will get this one. You don't need to do any mathematics. You can see it through. And then repeated this one, therefore degenerate and degenerate, okay? And we even know what is the value. Epsilon plus V, epsilon minus V. I'm taking V as negative as turns out to be the case, the integral. So if you do this, you put the electrons in, again, you will gain some energy. So this one also lower energy. So the last point is, this has even lower energy than doing 3 double bonds. That is called the delocalization energy. So we can define what is the delocalization energy. We have to do a wrong calculation and a right one, and then take the difference. So what we are claiming is this one has an even lower energy than this one. So what is the difference? The difference, the further gaining by delocalizing the electron is called the delocalization energy. And this theory is called the Huckel theory. A very early days of molecular physics, you know, 1927 or so, Dirac already did the many electron quantum mechanics. And starting from that point on, you have atoms and molecules physics developed rapidly. So that is the Huckel theory, and that could be applied to many different things. Then I would like to introduce a few names because some of you may be doing solar energy materials in your final year project, etc. Okay, and there are jargons that scare you off, but I would like to tell you that nothing fancy. One of them is something called the LUMO-HOMO difference. So that looks professional, but if you look at it, what it means is the following. That is the lowest unoccupied molecular orbitals. Okay, so of course it means these orbitals, right? Lowest but empty, unoccupied. What is HOMO? Highest occupied molecular orbitals. So, the material scientists, they look fancy after they know quantum mechanics. So, of course, the HOMO will refer to this two degenerate MOs because they are occupied, they are the highest energy being occupied. Now, what is the fancy of this difference? This is called the LUMO-HOMO difference. It is this energy difference. Okay? Why is it important? That plays the role of a gap. When we extend it to semiconductor, that will be the gap, energy gap of a semiconductor. What for? That will be the first energy that this thing will absorb, right? Because if you give that much h bar omega or h mu, there's no state for the electron to sit, okay? So if you supply that much energy, an electron could absorb and go up to the excited state, okay? And that will affect the optical properties or light absorption as well as light emission property of a material. And that is important, for example, in inventing or discovering solar energy materials. So next time when you see people throw at you some dragon LUMO-HOMO thing, you just laugh at them, okay? It's nothing. We can also extend our discussion on several other organic things. For example, this butadiene. Again, you can form double bond, single bond structure, or let the Z electron delocalize and compare the structure. Or else, that also further develop into carbon-60. So this buckyball thing, okay, you see it on the screen. So this is a Nobel Prize winning, awarded, I think it's a Nobel Prize in chemistry. But you see it, there's a lot of 120 degrees thing. So sp2 basically forming the skeleton, but it is not on a plane. When you flow it up to a three-dimensional thing, something interesting happens. In addition to this hexagonal thing, you need some pentagon structure in order to form a sphere, okay? And this is exactly the structure of a soccer ball. So basically, the structure, the skeleton forming the sphere is sp2 hybridization. Remember, each carbon, the black thing here, still has a pz sticking out and sticking into this curved surface. By our pi delocalization of electrons, actually 60 electrons are wandering on the surface and on the inner surface of this carbon-60 molecule. Okay, and many fancy things come out from that, well, including Nobel Prizes. And if you play soccer, next time you look at it, there are some pentagons, there. Otherwise, that will be a rugby. Let me see. The next fancy thing is just a flat layer. This is called graphene. In Chinese, it's called 石墨烯, 石墨烯. Okay, it's just one layer of carbon. So basically, in the pencils that you use, it is graphite. It is a form of carbon. If you peel one layer off, you will get this single layer of carbon. So it's very clearly, it is a sp2 hybridized skeleton, hexagonal all the way. Okay, but following our discussion, each carbon would have a pz sticking in and out of the layer. They should, again, maybe the electrons would like to delocalize. So this strong structure, in addition, there is some electrons living above and below it. That is the pz delocalized electrons. And now that is a bit of solid state physics. I cannot explain it to you in this course. That takes 2 hours or so. You need band structure, etc. But for the behavior of this pz electrons above and below this two-dimensional plane, the behavior is very peculiar, very strange. But you know, physicists find it happily strange. The behavior of this layer of electron has a certain energy momentum dependence. Just like free electron is p squared over 2m, right? But for electrons living on graphene, the behavior is like a cone. So the z-axis is the energy, the xy is px, py, because it's just two-dimensional structure. The momentum has two components only. But it is not parabolic as in ordinary p squared over 2m behavior. It happens to be two cones, one inverted and touch at a point. The next thing is to fill in the electrons. It so happens that it fills the lower cone completely and leaves the upper cone empty. So in this way, the LUMO-HOMO gap is 0. So it is a gapless material. One band is completely filled, the next is completely empty. It's a semiconductor. So that's why people will say graphene is a gapless semiconductor. But more happily, many physicists, now chemists, material scientists, find this to be a playground for QED system. For the reason, this cone means some linear dispersion. So this one is linear. Right? So you have epsilon being proportional to P. So it looks as if relativistically, the electron suddenly becomes massless fermion. Now, it is real electrons. It is the environment that this real electron lives in, the two-dimensional flat layer of graphene, that makes it behave like mass equals 0, but they are fermions. And it is a very fascinating topic, first found, I think, in the paper of Dirac. So suddenly, it looks like you have a cheap system in which the electron behaves relativistically. And there's a lot of solid state experiments now become a platform to explore quantum electrodynamic properties. And that's why graphene also got some Nobel Prizes. Okay, so at this point, I would like to take a break, but then today we need to do, you need to do something. I don't need to do anything. I must follow the Faculty of Science and the university's instruction. I will leave you 10 minutes from now on to do the online course evaluation. Now, first of all, do you receive an email with a link for this particular course to do the course evaluation? Yes, right? Now, according to the guideline, I must give you during class about 10 minutes for you to look at that link, click into it, and try to do it. The link is active till midnight tonight or tomorrow morning, okay? But according to the guideline, I must give you that time. So I will now stop my video, and then I will mute myself to leave the time to yourself alone to do the course evaluation. I will be back at around 10:36.